if a pilot is flying around the curve of the Earth, then he should be dipping the nose down every 5 minutes. He should be dipping the nose down to stay around the curve. But the thing that really got me interested was, as you say, the gyroscope. In a plane, there is an artificial horizon, okay, and it's based on a gyroscope. And if you spin a gyroscope on a surface, it will want to stay upright. You can twist and tilt the surface as much as you like, the gyroscope will stay upright. So if a plane has a gyroscope and it starts following the curve of the Earth, the gyroscope would stay upright, which means the artificial horizon will start to roll backwards. But it doesn't. That's absolute proof that a plane flies over a flat surface rather than a curved one. Because I asked the pilot on my last flight, do you ever notice the artificial horizon rolling backwards? He said, no, but the artificial horizon has complex electronics in it to make sure it knows where it is on the Earth and it compensates. But I went to the manufacturer of the artificial horizon, and they confirmed to me that it's completely mechanical, nothing electronic in it whatsoever. So it's literally just a gyroscope that can freely move. So that right there is proof to me that planes fly over a plane.
Okay, so this video is a bit of a follow-up to my previous two videos on gyroscopic navigation and all of that. I had a couple of points I wanted to add. The first one based on a comment that I just got, which just really blew me away. It's so simple, and yet it's... However, it seems you could also prove this by never leaving home, unless there's something I'm not understanding. If you were to just set the gyro in a gimbal base, where it could move freely, and then put it in motion with its axis in a vertical position, in the next 6 hours, wouldn't you see the axis slowly move to a horizontal position at the base, as the base rotates with the globe Earth? If it doesn't, then the Earth is not a spinning ball. Okay, so after taking a few seconds to let what he's saying absorb, I was like, holy cow, I think he's right. And that's pretty insane, because they don't ever talk about that, and you would think they would. I mean, right there in the film, he's saying that the gyroscope resists the pull of Earth. It does not stay in alignment with gravity or with the surface of the Earth, right? So that's when it goes into all the explanation of how the magnetic compass supposedly is what corrects it, and that's a whole nother thing, but I'll get into that in a minute. But it's totally true that if the gyroscope on the gimbal, when it's spun up fast enough, is going to resist the gravity of the Earth, when any kind of vehicle is moving around the ball, well, then the same thing is going to apply, just being in place on the surface of the Earth, and then the surface moves. And like you said, 6 hours, that's a quarter of the rotation day. That would give you a 90-degree difference. Should be pretty simple thing to prove. Now, of course, none of the you don't hear any of the Navy guys talking about this. And the crazy part is that, in a nutshell, what I think it means is that really the only way a gyroscopic navigation system could work is on a flat Earth. I mean, period. Because when you think about what they are saying, what are explaining about how the thing works, and that it does not stay aligned with the surface of the Earth, right? It always has to be. They're talking about how it needs to be adjusted when, you know, a gyroscope is in a vehicle that moves around the Earth. But at the same time, the Earth is constantly moving, so that's going to be throwing you out of alignment from the, you know, the true up and down as well. So how is a magnetic compass going to know how to, or anything else for that matter, to know how to adjust the gyroscope in relation to the Earth, accounting for both the motion, the movement of the vehicle, whether it's a plane or a sub or a ship or whatever, and the motion of the surface of the Earth around the center of the Earth, right? Which is supposedly where gravity is pulling everything down towards, right? So you've got two constantly changing factors, all the time, or at least one, because, you know, even if a gyroscope is sitting still, it's still moving on the surface of the Earth. But there's nothing to really, I mean, so the navigation system needs a navigation system. I mean, it's completely, it's absurd. And then when you take it a step further, I mean, obviously, according to the Copernican model, you know, the Earth is not the only thing that's moving. So if rigidity in space, this principle of rigidity in space, tells us that, you know, the gyroscope will resist, I mean, that clip says it will resist all forces put upon it, right? So gravity, and this bears out too because we know that when they use gyroscopes in jet planes, right, that so they always know which way is up is down, and they're doing all these dogfighting maneuvers and barrel rolls and subjecting the pilot and the plane to lots of G-forces. So if you're doing dogfighting maneuvers in a fighter jet, let's say, and you've got your gyroscope on its gimbals in there, so the pilot always knows which way is up and down and doesn't have to, look out his window. That means the gyroscope is resisting several G's of force. So if a gyroscope can function in that kind of an application, right, going hundreds of miles an hour, moving at crazy speeds and having to constantly stay level and resist that many G-forces on it, then what if it can resist that strong of gravitational forces, then it's resisting all of them, right? So not just the Earth's gravitation, but any of the other, gravities that are lesser than the Earth's that are supposedly functioning throughout the solar system. So I mean, my point is that there's lots of motions that are supposedly happening in a Copernican model, not just the Earth's rotation, but the Earth orbiting around the sun, the solar system rotating around the galaxy rotating around, the universe, and so on. So hypothetically, you would think that a truly precision functioning, military industrial grade gyroscope would be holding its fixed position, its rigidity in space, against all of those motions. So if you fired up a gyroscope, shouldn't you just see it doing all kinds of crazy things? I mean, shouldn't it just be not just moving 90 degrees over 6 hours, but it could be doing all kinds of motions because of all the different orbital things that are supposedly happening? But no, it stays in place, right? We're talking here, of course, we're talking about the kinds of gyroscopic navigation systems that they use, submarines and ships and things. We're not talking about toy gyroscopes, just for the record. But the other thing I was thinking too was just back on that video with the gyroscope and supposedly being corrected by the magnetic compass in that 1960 Navy training video. The more I've thought about that, the more absurd that is for a number of reasons. First of all, because a gyroscope is designed to maintain orientation in terms of several axes, and yet simply relying on a magnetic compass to tell you where north is well, that's going to tell you, that's only at the most going to give you, orientation for one axis, right? And and depending on where you are on the globe, north is always going to be in one direction, but it won't tell you like where the plane should be depending on where you are on the globe, because obviously if you're up in Alaska, it's going to be different than if you were down in South America or something. A magnetic compass doesn't point you directly at where the magnetic north is or the North Pole is. It only gives you it's basically a two-dimensional device, which is kind of worthless for supposedly calibrating a gyroscope. Not to mention, in this other video, it actually explains how you have several issues with magnetic compasses themselves in terms of magnetic variation and deviation, I believe. And anybody who's ever used a map and compass, like when they're out hiking, understands that magnetic north is not just this clean, easy thing that is the same wherever you are. Depending on where you are in the country or the world, magnetic north is always warped, so you always have to adjust for that in your calculations when using a compass, right? You always have to delineate, depending on where you are, like for the magnetic north. Now, how is a magnetic compass that is supposedly in a plane hooked up to a gyroscope going to know exactly where it is in the world to account for the amount of magnetic declination? That's the word, declination. To account for the correct amount of declination, to know where true north is, to then be able to reorient the gyroscope, all in split-second timing. It just gets ridiculous. So I think the bottom line is that gyroscopes, the only way that they could be of any use is on a completely flat plane, where up is always up, and sideways is always sideways, and down is always down. And otherwise it contradicts itself. The explanations they give for gyroscopes and how they function contradicts their own model. So there you go.
None of it makes sense. The problem is that we're taught as children, this ball earth lie. And, you might ask as a child, what about the people in Australia? They're standing on the bottom of the globe, won't they fall off? And your teacher says, no, gravity. And you go, oh, okay. And you never go back to that question. But when you go back to it as an adult and start looking at it with a critical eye, right, the whole thing falls apart. As you say, the globe is spinning at 1,000 miles an hour. Neil deGrasse Tyson, who's a leading astronomer in America,
I'm Neil deGrasse Tyson, bitch,
tells us that the Earth is not a perfect circle. It is actually an oblate spheroid. It's squashed, and wider at the equator. Yeah.
So Earth, throughout its life, even when it formed, it was spinning, and it got a little wider at the equator than it does at the poles. So it's not actually a sphere, it's oblate, and officially it's an oblate spheroid. That's what we call it. But not only that, it's slightly wider below the equator than above the equator.
A little chubbier.
A little chubbier.
Yeah.
Chubby's a good way. It's like pear-shaped.
So my question to him would be, why is there land at the equator? Because water will move more readily than rock. So if the Earth is spinning, the water will be collected at the equator. I mean, if you spin a wet tennis ball Okay, you spin the wet tennis ball, the water shoots off at the equator, essentially. So all the water will be gathered around the equator. So why is there land at the equator? Doesn't make any sense. The other thing that's about the spinning Earth is looking at the stars. Now, directly above the axis of spin is the pole star, Polaris, okay, directly over the North Pole. And we're told that the reason that all the stars spin around the North Star is because the Earth is spinning at 1,000 miles an hour. Okay, seems to make sense, because if you put a long exposure camera pointing at the North Star, you'll see the stars will make perfect circles around, perfect star trails. The only problem is the Earth is also orbiting the Sun at 67,000 miles an hour. Okay, the Sun is moving, dragging the Earth and all the planets up that way or that way at 600,000 miles an hour. So why do we see perfect circles? You know, because that's the slowest speed, that's slowest motion in that mix, and yet the Earth is moving 67 times faster that way and 600 times faster that way. So you should see the stars do all sorts of strange motions, but you don't. You only see them make these perfect circles. That tells me that it's the stars that are moving, not the Earth. It goes up. They will also say that if a sniper is trying to hit something a great distance, a couple of miles away, they have to take into consideration the spinning of the Earth, because they say that as the bullet leaves the muzzle of the gun, it's now independent of the rotation of the Earth. So, the Earth will spin away from where the bullet, and you have to take that into account. They say that about artillery shells as well, but it's not true. If that was true, a sniper would have to spend ages and ages calculating how to make that shot, and they don't. They literally take into consideration the wind and the elevation, and they don't take the Coriolis effect into consideration at all. Also, planes. If that works for bullets, if bullets, as soon as they leave the Earth, they're now independent of the spin, then why doesn't it work for planes? Yeah. There's a video on YouTube that actually tries to explain that the Coriolis effect works by using the example of a paper plane. You have to throw it. If you throw it north, the Earth will spin and the plane will land sort of east. But if you take the idea of a real plane, a plane would have to aim north to go east in that case. But that's not what happens. And if that was the case as well, planes would have to land on runways that are moving, and that would be impossible. But how is it that you can take a flight from London to New York and it will take exactly the same time as a flight from New York to London? Yeah, one's with the spin of the planet and the other one's against it. So it doesn't make sense. They'll say that the whole atmosphere is moving, with the planet, but that doesn't make sense either, because the atmosphere, say it's that thick, the top layer of the atmosphere will be moving slow, and as further you get in, will be moving faster. How, if everything is moving like that, how do you get a light breeze that blows against the spin of the planet? How do you get a breeze that goes from north to south? It just doesn't make sense. And again, science will give you calculations and esoteric ideas, but you can go out and look for yourself, and you'll see what makes sense and what doesn't.
We're adding a gyroscope. So we're adding a 3-axis gyro, which is fantastic. Pitch, roll, and yaw. Also rotation around gravity. Also rotation around gravity. Also rotation around gravity. And we've tied the gyro and the accelerometer and even the compass together to provide six-axis motion sensing. And we've got some new core motion APIs that you can call that give you extremely precise position information. And it's perfect for gaming. And one of the reasons it's perfect is because it's built into every iPhone 4, so you know it's there.
Inflated by blowing into the tube, and the light will illuminate when the battery comes in contact with the wire. The emergency exit sign located in front of the cabin. Open the wings, and in the rear of the cabin. Floor lighting will guide you to these exits. The end of these markings indicated to your bridge and exit. The safety instruction card is located in your seat bucket. Study this card before takeoff and make sure you know where to find the nearest exit. As part of standard safety procedures, the cabin lights will be dimmed during takeoff and landing. You will find the reading light in the panel above your head. Ladies and gentlemen, thank you for your attention, and on behalf of the entire crew, I wish you a pleasant flight.
mogelijk zien.
Dames en heren, welkom op de luchthaven van Eindhoven. Als we zitten met uw stoel in pas op de verlichting van de tekenstoring van Zuid is. Wees u voorzichtig bij het openen van de bagage en van handbagage uitvallen. Controleert u voor het uitstappen dat u geen persoonlijkheidsnummer wordt afgelaten. Rook in het luchthavengebouw is toegestaan u de daartoe aangegeven rookgebieden. Gezag voor de heerhuizen en belanding neemt afscheid van u. Wij danken u voor het vliegen met veel zaken en graag terug aan boord. Namens de hele bemanning wensen wij u een verblijf, een goede doorreis en wel thuis toe. Ladies and gentlemen, welkom to the airport of Eindhoven. Please remain seated with your seatbelt fastened until the fasten seatbelt sign is switched off.